Hello friends, I'm still talking about colligative properties, but this time I'm going to focus on the freezing point depression. Freezing point depression is the lowering of freezing point of the solvent by additional solute. Why is freezing point reduced or lowered when a solute is added to a given solvent? The particles of the solute interferes with the process of freezing up of a solvent because it prevents the molecules of the solvent being much closer to one another by covering some of them and prevent them getting in contact. And this reduces the intermolecular forces between the solvent molecules. And this requires a little bit lower temperature for a given substance to be frozen. It has got a lot of applications in our daily life. To mention some of them, during winter time, salt is used to remove ice from roadways to prevent accidents by the car tires sliding on the roads, on the ice that has covered the road. Antifreezes are also used for de-icing the control surfaces of aircraft. This is just to facilitate the aircraft, the airflow on the wings, on control surfaces of the aircraft when it is taking off. The glucols are used in vehicle radiator fluids to lower the freezing point of the liquid, hence making the fluid useful in winter. Otherwise, when it is in winter, it's very cold, and then the liquid that is in the car radiator, special water, would freeze up. But when you add glucose as a solute, it lowers the freezing point, and even though it is very cold, the liquid in the car radiator does not freeze up. So it can also be quantified. So the calculations related to freezing point depression are carried out in this way. So the freezing point depression is obtained by calculating the difference between the freezing point of the solvent minus the freezing point of the solution. As you can see, delta F, delta TF is the freezing point depression, and then T0 F is the freezing point of the pure solvent, and then TF is the freezing point of the solution. So the difference gives the freezing point depression. This is calculated in this way because the freezing point of the solvent is higher than the freezing point of the solution, which is the opposite for the case of boiling point elevation. For the boiling point elevation, we have seen that we take the boiling point of the solution minus the boiling point of the pure solvent. But this time we take the freezing point of the solvent because it's the one that's higher minus the freezing point of the solution because it's the one that's lower. Since it is a colligative property, as we have seen before, so it's directly proportional to the molarity. This is the formula where delta F is still boiling, freezing point depression, then which is equal to I, that's Van 't Hoff's factor, times molarity times the freezing point depression constant, Kf. So as I have said, the freezing point depression can be defined as the lowering in the freezing point of the solvent when a solute is added to it at a constant pressure. We are asked to calculate the freezing point of a solution made up of 400 grams of ethylene glycol, C2H6O2, in 500 grams of water. Kf of water is 1.8606 per molar, and its freezing point is 0 degrees Celsius. To solve this problem, we use the formula for finding the freezing point depression, that is delta TF, which is equal to Van 't Hoff's factor I, mass of the solute in grams times the freezing point elevation, depression constant Kf, divided by molar mass of the solute in gram per mole times the mass of the solvent in kilogram. So since ethylene glycol is an alcohol, it's non-ionizable solute, its Van 't Hoff's factor is equal to 1. And then when we substitute all the values in the relation we have above, we have 1 times 400 times 1.86 divided by 62.08, which is the molar mass of ethylene glycol, times 0.5, that's the mass of water in a kilogram. And this gives us the freezing point depression, that is equal to 24.0 degrees Celsius. So we are asked to calculate the freezing point of the solution. To find the freezing point of the solution, we use this relation, that freezing point depression equals to freezing point of the solvent, that's water, minus the freezing point of the solution. We have everything except from the freezing point of the solution, which is TF. Let's solve for the freezing point of the solution TF and substitute the values. We get TF, which is equal to 0 degrees Celsius minus 24.0 degrees Celsius, and then we get negative 24 degrees Celsius. As you can see, the freezing point of water is higher than the freezing point of the solution of ethylene glycol by 24 degrees Celsius. Number 2, we are asked to calculate the molecular weight of an unknown non-electrolyte substance if dissolving 1.42 grams in 25 of the pure benzene lowers the freezing point by 1.96 degrees Celsius. We are given the freezing point depression constant Kf for benzene, which is equal to 5.12 degrees Celsius per molar, and then we are asked to find the molecular weight, or the molar mass in other words. So we are going to use this relation of finding the freezing point depression, and as you can see, we have almost everything except from the molar mass. Let's transform this formula, and then we solve for the molar mass. We substitute all these values because they are there, and we find the molar mass, which is not known. And then when we substitute the values, we find that the molar mass equals to 1. That's the Van 't Hoff's factor, because we are told that it's a non-electrolyte. Its Van 't Hoff's factor is equal to 1, because it does not dissociate into ions in aqueous solution, in the solvent that's given here, which is benzene. And then times 1.42 times 5.12 divided by 1.96, that's the freezing point depression, times 0.025, that's the mass of the solvent in kilogram. And then now we have the molar mass of that unknown non-electrolyte substance, which is equal to 148.38 grams per mole. Thank you very much. We are coming next when we are talking about another colligative property. Thank you.